The Standard Model is the most successful theory ever written. It predicted particles decades before anyone saw them. It agrees with experiments to 12 decimal places. And yet, tonight, something is wrong with it. A muon wobbles in a magnet at Fermilab. A W boson weighs more than it should. Neutrinos carry a mass the theory says they cannot have. And somewhere in the math, the universe is missing 95% of itself. If you enjoy physics that reaches the edge of what we actually know, hit like and subscribe. It helps more than you think. What you're about to see is the gap where a deeper theory must be hiding. Settle in. We begin. Imagine a machine so accurate that if you used it to measure the distance between New York and Los Angeles, it would be off by less than the width of a single human hair. That is the Standard Model of particle physics. Every prediction it has ever made for more than 50 years has come true in the laboratory. Electrons, quarks, photons, the Higgs boson. It called them before anyone saw them. And when we built bigger and bigger machines to hunt for them, there they were, exactly where the math said they would be. And yet, if you ask a physicist whether the Standard Model is the final answer, they will quietly say no. Not because it has failed, because it has succeeded too well in a way that makes no sense. Here is the first strange thing. The Standard Model does not really predict the universe. It describes the universe, but only after you feed it a list of numbers. The mass of the electron, the mass of each quark, the strength of each force, the way particles mix into each other. You have to measure these numbers in an experiment, and then you hand them to the theory, and the theory takes over and works perfectly from there. But the theory itself has nothing to say about why the electron weighs what it weighs. Nothing. You could change the electron's mass in the equations and the math would still work. The equations do not care. Think of it like a cathedral. Every stone is perfectly cut. Every arch is perfectly balanced. But if you walk down into the crypt, you find that the entire weight of the building rests on about 17 blocks that someone simply placed there and said, "These are the right size because we measured them." There is no deeper reason. There is no foundation underneath the foundation. 17 numbers. That is roughly how many free parameters the Standard Model requires. You can argue the exact count depending on how you include neutrinos. But the point is that for a theory meant to describe everything at the smallest scales of reality, 17 is a lot of unexplained input. A truly fundamental theory, physicists have always suspected, should take in very little and produce very much. There is something else. The Standard Model does not contain gravity. The force you feel right now, pulling you into your chair, is simply not in the equations. Nobody has ever written a version of these equations that includes gravity and behaves properly at small scales. Every attempt produces infinities, which is the maths way of saying you have broken something. So you have a theory that explains 3 of the 4 known forces, describes every particle you can hit with a collider, agrees with experiment to a precision that borders on absurd and yet cannot tell you where its own numbers come from, cannot include gravity, and cannot explain 95% of the universe's contents. That last part is not a typo. 95%. We will get there. For now, the setup is this. The Standard Model is not wrong. It is incomplete in a very specific, very dangerous way. And the cracks, the places where it visibly struggles, are starting to show. The first crack involves a tiny particle that behaves like a heavier version of the electron. It has a wobble nobody can fully account for. There is a particle called the muon. It is like an electron in almost every way. Same charge, same spin, Same behaviour in electric and magnetic fields. The only real difference is that the muon is about 200 times heavier and it does not live long. A muon left alone will survive for about 2/millionths of a second before breaking apart into lighter particles. In the time it takes you to blink, quadrillions of muons have come into existence somewhere in Earth's atmosphere and disappeared again. Now, if you take a muon and put it inside a magnetic field, something interesting happens. The muon spins, and because it is electrically charged and spinning, it behaves like a tiny magnet. That tiny magnet tries to line up with the big magnetic field you have placed it in, but it does not just sit still. It wobbles, the way a spinning top wobbles when you tilt it. How fast it wobbles is the entire story. The standard model can predict that wobble. In fact, it predicts it with absolutely ferocious precision, using a chain of calculations that accounts for the muon itself, plus the ghostly cloud of other particles that briefly pop in and out of existence around it. Every electron, every photon, every quark in the vacuum around the muon tugs on it a tiny amount and changes its wobble by a tiny amount. The theory adds all these tugs together and gives you a number. Then you go to a laboratory at Fermilab outside Chicago. You build an enormous ring 50 feet across, filled with the strongest precision magnetic field anyone has ever built. You shoot billions of muons into the ring and measure their wobble for years, and you compare. For more than 20 years, the measured wobble and the predicted wobble did not match. Not by much, a difference that showed up in the 9th or 10th decimal place. But in a theory that is usually accurate to 12 decimal places, a mismatch at the 10th is a siren going off in the distance. Something, somewhere, was tugging on the muon that the standard model did not know about. A new particle, perhaps, a new force, something hiding just outside the edges of the theory. The excitement built for years. Each new data run made the discrepancy sharper. By the early 2020s, the experimental side was closing in on a gap that would have meant a genuine discovery of new physics. Then, in June of 2025, Fermilab published the final result from the muon G-2 experiment. The measurement was spectacular. Precision better than the original design goal, a pinpoint value that would stand for a generation. And at roughly the same time, the theorists updated their side of the calculation using a different computational method, one that simulates the strong force directly on supercomputers. The theoretical prediction shifted. It moved toward the experimental value. The gap closed, not all the way. There is still a sliver of disagreement, and a lively fight about which theoretical calculation to trust. But the clean, dramatic anomaly that dominated headlines for a decade had quietly become a technical dispute. This is where the standard model really fights you. It flirts with failure and then steps back. The muon's wobble is not the crack, but something heavier, something far more stubborn, is pulling at the theory from another direction entirely. There is a particle called the W boson. You have never felt it directly, but without it, you would not exist. The W is the messenger of the weak force, the force that allows one kind of quark to turn into another and lets the sun shine by fusing hydrogen in its core. When a neutron inside an atom decays into a proton, a W boson carries away the transaction. It appears, it vanishes, and the universe reshuffles. The W has a mass, not a small one. A single W boson weighs about 80 times as much as a proton, which makes it one of the heaviest fundamental particles we know about, and because the standard model is stitched together so tightly, the mass of the W is not free to be anything. Given the mass of the top quark, the mass of the Higgs boson, and a handful of other measured quantities, The theory predicts the W's mass to within a few parts in 10,000. Measure those other particles carefully, plug them in, and the W's mass pops out of the equations like a receipt from a cash register. So in 2022, when a team of physicists at Fermilab published the most precise measurement ever made of the W boson's mass, the whole field paid attention. They'd spent almost a decade analysing data from an older experiment called CDF. They were careful. They were thorough. They used events from the early 2000s and refined the calibration year after year. Their number came out higher than the standard model's prediction, not a little higher. 7 standard deviations higher, which in the language of physics means the probability of this happening by chance is so small you would not bet your lunch on it, much less your career. If the CDF measurement is right, something outside the standard model is adding mass to the W boson, a new particle running quietly in the quantum background. A new interaction the theory does not know about. The W would be the first clean signal of physics the standard model cannot contain. Here is where it gets uncomfortable in the honest way physics actually works. Other experiments have measured the W's mass too. The LHC at CERN has measured it. The old LEP collider measured it. The D0 experiment, which ran right next door to CDF, measured it. Most of these results cluster near the standard model prediction. CDF sits alone, stubbornly high, with an uncertainty so small it should not be possible to reconcile with the others through simple statistical noise. So either CDF made a subtle systematic error that every independent review has so far failed to find, or everyone else is slightly off, and CDF is telling us a truth the rest could not see. Physicists have spent years picking the CDF analysis apart. They have checked the detector calibration, the background subtraction, the simulation software. The result has not gone away. This is what a real crack in a theory looks like, not a dramatic collapse. A single measurement made carefully that refuses to agree with anyone else's in a quantity that should agree if the theory is complete. Meanwhile, another crack was opening in a different direction entirely, involving a particle that was supposed to behave the same whether it was light or heavy. It did not. There is a rule buried inside the standard model that almost sounds like a promise. The rule is called lepton universality, and it says something simple. There are 3 charged particles that work like the electron itself, the muon, which is heavier, and the tau, which is heavier still. According to the theory, these 3 particles are identical in every way except for their mass. They feel the same forces with the same strength. They couple to the weak force identically. They couple to photons identically. The only reason they look different in an experiment is that they carry different amounts of weight. Think of 3 runners who are exactly equal in skill, but one is wearing a backpack and another is wearing a much heavier backpack. They run slower, yes. But the way they run, the muscles they use, the form they take, is the same. That is lepton universality. So if you have a particle that can decay into different kinds of leptons, the theory makes a clean prediction. The rate at which it decays into electrons and the rate at which it decays into muons should be almost exactly equal once you adjust for the fact that muons are heavier. Enter a particle called the meson. It contains a heavy quark called the bottom quark, which can transform into a lighter quark by emitting a pair of leptons. Sometimes it emits 2 electrons, sometimes it emits 2 muons. According to the standard model, these 2 possibilities should happen at the same rate. The LHC-B experiment at CERN spent years measuring the ratio. They called it R sub K. The prediction was almost exactly 1. If the measurement came out as 1, the standard model held. If it came out lower, something strange was happening to the muons, or something strange was being hidden from the electrons, or a new particle was secretly interfering with the decay. For years, R sub k kept coming in low, around 0.8, with a statistical significance that kept creeping upward until it reached 3 standard deviations, which is the threshold where physicists start to sit up straight. Other related measurements kept drifting in the same direction. A pattern was forming across many decays, all pointing to the same conclusion. Electrons and muons might not be equivalent after all. Theorists wrote hundreds of papers proposing new particles called leptoquarks to explain the gap. Then, in late 2022, LHCb reanalyzed the data with a better understanding of how their detector confused certain particles for others. They corrected a systematic error. The ratio moved back toward 1. The anomaly shrank from 3 standard deviations to less than 1. Lepton universality survived, but not cleanly. Related decays involving the tau lepton and the bottom quark transforming to a charm quark still show a persistent deviation from the standard model prediction. The world average is still a little off, not as dramatic as R sub k was at its peak, but not gone. This is the pattern you will see again and again. Anomalies appear, hold for a few years, and either resolve or hover at the edge of significance without ever quite being confirmed. The theory bends and does not break, and then you get to a particle that the standard model insists cannot have a mass at all, even though it demonstrably does. The neutrino is the ghost of the particle world. It carries no electric charge. It barely interacts with anything. Right now, trillions of neutrinos from the sun are passing through your body every second, and essentially none of them are touching a single atom inside you. If you built a wall of solid lead 1 light-year thick, a neutrino would still have about a 50-50 chance of sailing through it without noticing. The standard model has a very clean thing to say about neutrinos. It says they are massless. In the original theory, written down in the 1960s and 70s, the neutrino has exactly 0 weight. It travels at the speed of light. It has one specific handedness, meaning it spins in one direction relative to its motion, and there is no such thing as a right-handed version of it. This is not a soft prediction. It is not a we think or we estimate. The equations are structured so that a neutrino mass term simply cannot be written down using only the ingredients the standard model has. To give the neutrino a mass, you would need a particle the theory does not contain, or a mechanism it does not include. Now here is the trouble. We know without question that neutrinos have mass. We know this because of a phenomenon called neutrino oscillation. When a neutrino is created, it comes in one of 3 varieties called flavors. There is the electron neutrino, the muon neutrino, and the tau neutrino. A nuclear reaction in the Sun, for example, produces electron neutrinos. Thousands of those electron neutrinos leave the Sun and travel toward Earth. By the time they arrive at a detector buried under a mountain in Japan, or in the rocks of Sudbury, Canada, roughly 2/3 of them have turned into a different flavor. They started as electron neutrinos. They arrived as muon and tau neutrinos. They changed mid-flight from one kind of particle into another. This only works if the 3 flavors are actually mixtures of 3 different mass states. The electron neutrino you detect is not really a single pure thing. It is a superposition, a blend of 3 underlying neutrinos with 3 slightly different masses. As the neutrino travels, these 3 mass components oscillate at slightly different rates, and the blend shifts. What was mostly electron becomes mostly muon, then tau, then electron again. The only way this happens is if at least 2 of the 3 masses are different, and if they are different, then at least 2 of them are not 0. the neutrino has mass, the standard model as originally written forbids this. Period. The theory can be patched, and it has been. Physicists have added extra terms, introduced speculative particles called right-handed neutrinos, borrowed a mathematical trick called the seesaw mechanism. All of these patches work in the sense that they produce numbers that match experiments, but none of them are part of the original standard model. Each one is an extension, an addition, a sign that the theory was never complete. The neutrino mass is not a small anomaly. It is proof, accepted by everyone in the field, that the standard model is missing something fundamental. And how the three neutrino masses are arranged, which one is heaviest, which is lightest, is a question that may decide how the early universe actually worked. 3 neutrinos, 3 masses. The standard model as originally written has nothing to say about any of them, but nature does. And we still do not know, as of today, the order they come in. Think of 3 weights on a shelf. You know 2 of the weights are close together, and one is noticeably apart from the other 2. You know the difference between the close pair. You know the gap to the third. But you do not know whether the lone one sits above the pair or below it. That is the situation with neutrino masses, and it is called the mass hierarchy problem. In the normal hierarchy, the lightest neutrino is at the bottom, followed by a middle one a tiny bit heavier, and then a third neutrino sitting noticeably above them both. In the inverted hierarchy, it flips. 2 heavier neutrinos sit close together at the top, and a single light one sits alone at the bottom. Both arrangements are consistent with everything we have measured so far. This sounds like a detail. It is not. The hierarchy decides which extensions of the standard model are viable, which theories of the early universe make sense, and even what happened in the first second after the Big Bang. Here is why it matters so much. Neutrinos were produced in unimaginable numbers in the first moments after the Big Bang. The universe is still filled with them. Every cubic inch of space around you, right now, contains roughly 330 neutrinos left over from that time. They're called the cosmic neutrino background, and they've been drifting through the universe for nearly 14 billion years. Because they have mass, they affect how matter clump together to form galaxies. A heavier neutrino smears out structure more. A lighter one lets it clump tighter. By looking at how galaxies are distributed across the sky, cosmologists can place limits on the total mass of all 3 neutrinos combined. Current measurements from cosmic surveys suggest this total sum is very small. So small that some analyses are starting to favour the normal hierarchy over the inverted one, and in a few cases the measurements are pushing so hard that they almost conflict with the minimum mass required if at least 2 neutrinos must be non-zero. If that tension holds up, it would mean the universe, on its largest scales, disagrees with laboratory measurements of neutrino oscillations on the smallest scales. That disagreement will be a second independent crack in our current picture. Meanwhile, huge experiments have been built to settle the hierarchy directly. In China, a detector called JUNO, buried deep underground, is watching antineutrinos from 2 nuclear power plants roughly 50 kilometers away. By measuring how the antineutrino flavors oscillate over that precise distance, Juno should be able to tell whether the lone neutrino sits above or below the pair. In the United States, the Dune experiment is building a detector that will catch neutrinos fired from Fermilab, 1,200 kilometers through solid rock, to an underground laboratory in South Dakota. The answer matters because the hierarchy tells us how neutrinos got their masses in the first place. Different theoretical mechanisms favor different hierarchies. Picking the right arrangement narrows the field of possible theories that could replace or extend the standard model, and the reason neutrinos matter so much for what comes next is that they may be responsible for the single most important accident in cosmic history. The accident that let matter exist at all. When the universe was very young, it was a furnace of pure energy. Particles came into existence and vanished again, continuously, at temperatures and densities that are hard to even describe in ordinary language. But the one rule everyone expected the early universe to follow is beautifully simple. Energy makes matter and antimatter in equal amounts, always. When a photon has enough energy to produce a particle, it produces a particle-antiparticle pair. One matter particle and one mirror image partner with the opposite charge and opposite internal properties. In the laboratory, every time we have tried, this is exactly what happens. Create an electron, and you also create a positron. Create a quark, and you create an antiquark. The ledger balances. So in the first tiny fraction of a second after the Big Bang, the universe should have been filled with matter and antimatter in perfectly equal amounts. And as the universe cooled, matter and antimatter should have found each other, annihilated and converted back into light. The universe should have ended up as a vast empty expanse of photons, with essentially no surviving matter anywhere. That is not what happened. You are sitting here. Atoms exist. Galaxies exist. The planet you're on is made of matter, and as far as we can tell, so is every other galaxy we have ever observed. There are no antimatter stars anywhere in the visible universe. If there were, we would see the boundary where antimatter galaxies meet matter galaxies, because the collision would produce a flood of gamma rays visible across cosmic distances. We do not see it. Somehow, the early universe made slightly more matter than antimatter. The imbalance was minuscule, roughly one extra particle of matter for every billion particle-antiparticle pairs. That billion pairs annihilated back into photons, leaving behind a tiny surplus of matter. That surplus is everything you see: your body, the chair, the earth, the sun, the stars, 1 part in a billion. That is how close you came to not existing. Now the question physicists have been chasing for 70 years is this: what broke the symmetry? What made the early universe prefer matter over antimatter by that tiny crucial amount? In 1967, the Russian physicist Andrei Sakharov wrote down 3 conditions that any successful answer must satisfy. First, some process in the early universe must have created more baryons, which are the heavy particles like protons and neutrons, than antibaryons. Second, the laws of physics must slightly prefer matter to antimatter, a preference called CP violation. Third, the universe must have gone through a period where it was not in thermal equilibrium, so that the imbalance could be locked in before it was erased. The standard model contains some CP violation. It was discovered in the 1960s in the decay of strange particles. It has since been measured in many different systems. It is real, it is there, and it is nowhere near large enough to explain the universe. When theorists calculate the amount of matter-antimatter asymmetry the standard model's CP violation could produce in the early universe, they get a number roughly 1 billion times too small. 1 billion! The standard model can explain maybe 1 part in 1 trillion. The universe needs 1 part in 1 billion. So the preference that let you exist came from somewhere outside the theory, and finding it is one of the central missions of modern physics. So the standard model has some matter-antimatter asymmetry built in, but only about 1 billionth of what the universe needs. That means there must be another source of asymmetry, hiding somewhere in physics beyond the standard model. Physicists have spent decades trying to figure out where. The leading candidate goes by a slightly menacing name, leptogenesis. The idea is that the asymmetry did not start among the quarks and protons we see today. It started among neutrinos, and specifically among a kind of neutrino the standard model does not contain. Here is the reasoning, as cleanly as anyone can state it. If you want to give ordinary neutrinos a small mass, the most elegant mechanism involves introducing 3 new, very heavy neutrinos that never appear in everyday physics. They're called right-handed neutrinos, or sometimes sterile neutrinos in certain contexts, and they would have existed only in the extreme heat of the very early universe. Ordinary neutrinos acquire their tiny masses through a kind of mathematical dance with these heavy partners, pushing the everyday neutrino masses down while pushing the partner masses up. This is the seesaw mechanism, and it is the most popular explanation for why neutrinos weigh almost nothing rather than nothing at all. Now, these heavy neutrinos would have been created in the first moments after the Big Bang. As the universe expanded and cooled, they would have decayed, and here is the key. If their decay involved some asymmetry, if they preferred to decay into leptons slightly more often than into antileptons, then the early universe would have developed a small surplus of leptons over antileptons. Lepton is the family name for the electron and the neutrino, and a few of their cousins. So an excess of leptons means an excess of particles that carry something physicists call lepton number. So far, this only produces a lepton asymmetry. It does not explain the excess of protons and neutrons, which are made of quarks. But the standard model itself contains a strange, almost magical process called a sphaleron. At the extremely high temperatures of the early universe, sphalerons could convert lepton asymmetry into quark asymmetry, shuffling the imbalance from one family of particles to the other. By the time the universe cooled below a certain threshold, the original lepton surplus from the heavy neutrino decays had been partially converted into an excess of quarks over antiquarks. Those extra quarks eventually bound themselves into the protons and neutrons that make up every atom in your body. This entire story is beautiful, consistent, and almost impossible to verify directly. The heavy neutrinos required for leptogenesis would weigh perhaps 1 trillion times more than anything we can produce in a particle collider. Their existence is inferred, not observed. But there are indirect tests. If neutrinos are their own antiparticles, a property called being Majorana, then the seesaw mechanism fits naturally. And if neutrinos are Majorana, then there is a very rare nuclear process called neutrinoless double beta decay that could in principle happen. Experiments around the world are watching kilograms of specially prepared material, waiting for a single such event. None has been seen. Yet, the extra asymmetry that lets you exist may come from particles we will never directly detect, producing a ripple that was amplified by physics still being tested. And now we reach the part of the theory where the standard model stops being a little incomplete and starts being truly silent. You can walk outside on a clear night and look up at a galaxy. Not a star. A whole galaxy, perhaps the Andromeda galaxy, faintly visible as a smudge of light. That smudge contains roughly 1 trillion stars, along with clouds of gas and dust, all spinning around a common centre. In the 1970s, an astronomer named Vera Rubin measured how fast the stars in spiral galaxies were moving. She expected to see what our solar system shows us. In the solar system, the planets close to the Sun orbit fast, and the planets far from the Sun orbit slowly. That makes sense. Most of the mass is concentrated in the Sun, so the gravitational pull drops off with distance, and the outer planets feel a weaker tug. Galaxies were supposed to behave the same way. Stars near the center should orbit quickly. Stars in the outskirts should crawl. They did not crawl. The outer stars were moving almost as fast as the inner ones. Every galaxy Rubin measured showed the same pattern. It was as if something was pulling on the outer stars, something invisible, something more massive than all the visible matter in the galaxy combined. That was the first clean evidence for dark matter. Since then, the evidence has piled up from every direction. The way galaxies cluster together, the way light bends around massive objects, a phenomenon called gravitational lensing, the pattern of tiny temperature variations in the cosmic microwave background, the afterglow of the Big Bang, the way the earliest galaxies formed faster than they should have been able to, given only ordinary matter's gravitational pull. All of these independent measurements, using different instruments and different physics, converge on the same number. The universe contains about 5 times more dark matter than ordinary matter. Every atom in your body, every star, every planet, every gas cloud, all of it together accounts for less than 20% of the matter in the universe. The other 85% is something we have never touched, never trapped, never seen, and cannot currently identify. And the Standard Model says nothing about it. 0 particles in the Standard Model fit the description of dark matter. It cannot be neutrinos, because neutrinos are too light and too fast. They would have zoomed out of forming galaxies rather than clumping into them. It cannot be any of the quarks or electrons, because those would absorb and emit light, and dark matter clearly does not. It cannot be antimatter, because antimatter would have annihilated with ordinary matter long ago. Whatever dark matter is, it is something new, a particle, or a family of particles that interacts with gravity but almost nothing else. It passes through ordinary matter like a ghost, occupying vast halos around every galaxy, dragging the visible matter into the gravitational wells it creates. This is the single largest failure of the Standard Model, not a subtle disagreement at the 10th decimal place, a gap of 85%, a complete absence of explanation for the dominant form of matter in the universe. Theorists have proposed many candidates. The leading possibilities include something called a WIMP, weakly interacting massive particles that might weigh roughly 100 times more than a proton. Another possibility is axions, extremely light particles invented to solve a completely different problem. A third is sterile neutrinos, heavier cousins of ordinary neutrinos. For decades, experiments have been hunting for the first of these. Deep underneath the mountains of Italy, inside a working gold mine in South Dakota, at the bottom of an old iron mine in Ontario, physicists have built some of the quietest places on Earth. They are quiet in a very particular sense. They are shielded from cosmic rays by thousands of feet of solid rock. Every surface inside them is scrubbed of radioactive contamination. The detectors sit inside tanks of ultra-pure water, wrapped in lead, cooled to nearly absolute zero. These laboratories are waiting. They're waiting for one of the billions of dark matter particles that should be streaming through the Earth every second to finally bump into an atomic nucleus. The idea is this: if dark matter is made of WIMPs, weakly interacting massive particles, then even though such particles almost never collide with anything, once in a long while one of them will pass close enough to the nucleus of an atom that it will give that nucleus a tiny kick. The nucleus will recoil. The recoil will deposit a small amount of energy in the detector. That energy will show up as a flash of light, or a puff of heat, or a whisper of ionized charge. A single event would be a discovery. Experiments have been running for more than 30 years. XeNON1T and its successor, XeNONNT in Italy, use huge tanks of liquid xenon. Lux and LZ in South Dakota use the same principle with bigger detectors. Panda X in China operates on the same idea. These detectors have been scaled up from kilograms to tons of target material. The sensitivity has improved by factors of 100, then 1,000, then 10,000, and the result so far has been silence. No confirmed dark matter detection, not once, in any of the major experiments. The only flickers that have ever been claimed were either ruled out by follow-up experiments or explained by ordinary background effects. This silence is meaningful. It is telling us something. Each time the experiments do not see dark matter, they rule out a chunk of possible WIMP parameters. The mass range, the interaction strength, the coupling to ordinary matter, whole regions of possibility get eliminated. At this point, the most natural versions of WIMP dark matter, the versions that emerge from the simplest extensions of the standard model, have been largely excluded. The particle we thought was most likely is running out of places to hide. This is starting to push physicists toward other candidates, axions, which will be detected by different means involving high-precision magnetic cavities and sensitive microwave receivers. Experiments like ADMX at the University of Washington are scanning through possible axion frequencies, looking for the faint signal of axions converting into photons inside a strong magnetic field. A different class of experiments is looking for dark matter that is much lighter than a WIMP, in the range of a few electron volts or even less, requiring completely different detector technology. And some physicists have started to wonder whether dark matter might not be a particle at all, whether it might be something stranger, a modification of gravity that only becomes noticeable on galactic scales, a form of matter that lives in extra dimensions we cannot directly access. Primordial black holes left over from the Big Bang, each one weighing as much as an asteroid. The silence underground is not a failure, it is a clue that whatever dark matter is, it is not what we most naturally expected, and the standard model is not going to reach it from its current foundation. Because while dark matter is the 85% of matter we cannot explain, there is another substance, even more abundant, that fills the universe. It is accelerating cosmic expansion, and nobody knows what it is. Add up everything in the universe, all the atoms in all the stars, all the gas between stars, all the dark matter in all the galactic halos, everything that has mass. That total accounts for about 30% of what is in the universe. The other 70% is not matter at all. It is something called dark energy. And it was discovered, almost by accident, in 1998, when two independent teams of astronomers were doing a completely different experiment. They were measuring how the expansion of the universe was slowing down. Every cosmologist at the time assumed the expansion had to be slowing down because gravity pulls matter together. The question was just how much. The teams used a type of exploding star called a Type 1a supernova. These supernovae are useful because they always explode with roughly the same intrinsic brightness. If you know how bright something actually is and how bright it looks from Earth, you can figure out how far away it is. By measuring the distance to dozens of these supernovae and comparing it to how fast they were moving away from us, the teams could map the expansion history of the universe. What they found did not match anyone's expectations. The expansion of the universe was not slowing down, it was speeding up. Something was pushing space itself apart. Something was overpowering the inward gravitational pull of all the matter and dark matter in the universe combined. And it was winning increasingly as the universe aged and spread out. They called it dark energy. The name is a placeholder. Nobody knows what it actually is. The simplest mathematical description is something called the cosmological constant. It appears in Einstein's equations of general relativity as a number that represents the energy density of empty space itself. According to this picture, empty space is not really empty. It has a small positive energy associated with it, and that energy acts like a kind of anti-gravity on the largest scales, pushing galaxies apart even as gravity tries to pull them together. The cosmological constant fits the data extremely well. Every large-scale measurement of the universe's geometry and expansion history is consistent with dark energy being a simple cosmological constant at the level of current precision. The trouble is not with the fit. The trouble is that nobody knows why the cosmological constant has the value it does. And when physicists try to predict its value using the Standard Model and quantum field theory, they get an answer that is stunningly, catastrophically wrong. Dark energy accounts for about 70% of the universe's total energy content. Combined with dark matter at about 25%, that means ordinary matter, the matter described by the Standard Model, the matter we have spent a century studying with colliders and detectors, makes up only about 5% of everything. 5%. That is the universe the Standard Model describes. Everything else, almost all of reality, is stuff the theory cannot touch. And the attempt to calculate the cosmological constant from first principles produces the single most embarrassing result in the history of physics. A calculation so wrong, so wildly off, that it has its own name. The cosmological constant problem. Empty space is not empty. This is one of the strangest truths of quantum physics, and it has been confirmed in laboratory after laboratory for decades. At the smallest scales, the vacuum is a seething foam of activity. Particle-antiparticle pairs pop into existence, live for an unimaginably short moment, and annihilate back into nothing, over and over, everywhere, always. They are called virtual particles, and although they do not persist long enough to be directly detected, their indirect effects are real. They change the magnetic moment of the electron. They produce a tiny force between two close metal plates in a vacuum, called the Casimir effect. They contribute to the way the muon wobbles in a magnetic field. All of this has been measured. The quantum vacuum is not a metaphor. It is a physical thing. Now here is the question that broke cosmology. If the quantum vacuum has all this activity happening inside it, then empty space has an energy. You can add up all the virtual particle pairs, all their fluctuations, all their contributions, and calculate what the energy density of empty space ought to be according to quantum field theory, according to the very framework that underlies the Standard Model. When you do this calculation, the answer you get is absolutely enormous. So enormous that if the vacuum really had that much energy, the cosmological constant would be so large that the universe would have ripped itself apart in the first fraction of a second after the Big Bang. No galaxies could form, no stars, no planets. Everything would have been blasted apart by the anti-gravitational push of the vacuum before anything interesting happened. But we observe dark energy to be about the size of the cosmological constant. It is real. It is non-zero. It is accelerating the expansion of the universe, and the observed value is smaller than the quantum field theory prediction by a factor of roughly 10 to the 120th power. That is a 1 followed by 120 zeros. The prediction is off by that much. To put this in perspective, there is no scale in science where a theoretical prediction is this wrong. If you predicted the weight of an electron and got it wrong by a factor of 10 to the 120th, you would be off by more than the mass of every particle in the observable universe, multiplied together many times over. This is not a small discrepancy. This is the single worst prediction in the history of physics, and the standard model has no way to fix it. The only explanations that have been proposed require mechanisms outside the theory. Perhaps there is a cancellation, something called supersymmetry, where every particle has a heavier partner whose vacuum contributions exactly cancel the original. Supersymmetry would reduce the prediction to something more reasonable, but decades of searches at the LHC have failed to find any sign of supersymmetric partners, at least within reach of current colliders. Another idea is that there are many universes, each with a different cosmological constant, and we live in the rare one where the value happens to be small enough to allow galaxies and stars to form. This is called the multiverse explanation, and while some physicists find it compelling, others consider it closer to philosophy than physics because it is extremely difficult to test. For now, the cosmological constant problem sits on the desk of theoretical physics like an unpaid bill. Everyone acknowledges it. Nobody knows how to pay it. And the same kind of fine-tuning shows up in one more place, the Higgs boson. The Higgs boson is the particle that gives other particles their mass. You've probably heard this phrase many times, and it is almost right. More precisely, the Higgs field fills all of space, and the other particles in the standard model interact with that field to varying degrees. Particles that interact strongly with the Higgs field behave as if they have a large mass. Particles that interact weakly with it behave as if they have a small mass. The photon, which does not interact with the Higgs field at all, has no mass and travels at the speed of light. When the LHC discovered the Higgs boson in 2012, it was one of the great moments in science. The last missing piece of the standard model fell into place. The Higgs weighed about 125 times more than a proton, a clean, measured value. And that number is where a new problem begins. The mass of the Higgs, in quantum field theory, is not a protected quantity. Unlike the mass of a photon, which is exactly zero because of the deep symmetries of electromagnetism, the mass of the Higgs boson has no such protection. It is sensitive to everything. Every particle in the universe, real or virtual, contributes a correction to the Higgs mass through quantum loops. Virtual top quarks push the Higgs mass up. Virtual electrons nudge it. Virtual gauge bosons pull on it. When you add up all these corrections and you include the most important contributions from particles at the highest energies, the natural value for the Higgs mass should be roughly the Planck scale. The Planck scale is the energy at which gravity becomes as strong as the other forces. It is about 10 to the 19th times larger than the mass of the proton. In other words, the Higgs mass should naturally be around 1,000,000 trillion times heavier than what we actually measure. It is not. It is light. It is right there at 125 times the proton's mass, sitting at a scale where human colliders can reach it. For the Higgs to be this light, there must be an extraordinarily precise cancellation happening between all the different quantum contributions. Positive contributions must cancel almost exactly with negative contributions, over and over, at many orders of magnitude, leaving behind a small residue that is what we observe. The amount of cancellation required is staggering. Numbers that are each enormously large must cancel each other out to roughly 30 decimal places, leaving behind a residue that is minuscule by comparison. If the numbers did not cancel to this precision, the Higgs boson would be vastly heavier, and the entire structure of particle physics, atoms, chemistry, and biology would be impossible. This is called the hierarchy problem. Not because something is hierarchical in the normal sense, but because there is an enormous gap, a hierarchy, between the natural scale at which the Higgs should sit and the scale at which it actually sits, and the standard model provides no mechanism to explain that gap. To most physicists, this kind of precise cancellation without an underlying reason feels wrong. It feels like a clue. Nature appears to be hiding something, some deeper symmetry, some additional mechanism, some new set of particles that forces the cancellation to happen automatically rather than by coincidence. The leading candidate for that mechanism has been searched for relentlessly at the largest collider ever built, and it has not shown up. For almost 50 years, the favourite solution to the hierarchy problem was an idea called supersymmetry. It is an elegant idea. It is almost too elegant, which is part of why so many physicists fell in love with it, and part of why its absence has been so painful. Here is the core of it. In the standard model, there are two fundamentally different kinds of particles. Fermions, like electrons and quarks, which are the building blocks of matter, and bosons, like photons and Higgs bosons, which carry forces. Fermions are standoffish. No two identical fermions can occupy the same quantum state, which is why atoms have structure and why solid matter does not collapse into a single point. Bosons are social. They like to pile into the same state, which is why lasers work and why the Higgs field can fill all of space uniformly. Supersymmetry proposes that every fermion has a boson partner and every boson has a fermion partner. The electron would have a partner called the selectron. The photon would have a partner called the photino. The quark would have a partner called the squark. These partner particles would behave almost exactly like their counterparts, except with the opposite type of statistics. Fermion becomes boson, boson becomes fermion. If supersymmetry were exact, the partner particles would have exactly the same masses as the originals. That is clearly not the case, since we have never seen a selectron with the same mass as the electron. So supersymmetry must be broken, with the partners having much larger masses than their counterparts. Now here is the magical thing about supersymmetry. It solves the hierarchy problem almost automatically. Remember that the Higgs mass gets enormous corrections from virtual particles, and those corrections have to cancel to absurd precision. In supersymmetry, every time a fermion contributes a correction to the Higgs mass with one sign, the fermion's partner, boson, contributes a correction with the opposite sign. They cancel, not by coincidence, but by design. If supersymmetry exists, and if the partner particles are not too much heavier than the particles we already know, the hierarchy problem dissolves. No fine-tuning, no coincidence. The Higgs is naturally light because of a deep symmetry in the structure of physics. Supersymmetry also has other appeals. It makes the strengths of the three standard model forces converge to a single value at high energies, which is what you would expect if they were different aspects of a single unified force. It offers a natural candidate for dark matter, the lightest stable supersymmetric particle. It makes string theory work in a mathematically consistent way. For decades, particle physicists assumed supersymmetry was just waiting to be found. The LHC was designed, in part, to find it. The LHC found the Higgs. It did not find supersymmetry, not at the energies it has reached so far, not in any search that has been conducted. The simplest, most natural versions of supersymmetry required partner particles at masses the LHC should have been able to produce. Those versions have been ruled out. The remaining versions require the partners to be heavier, which means the hierarchy problem is not solved as cleanly, because the cancellation has to happen at a higher scale, which requires its own fine-tuning to work. The theory is not dead, but it is wounded, and the longer the LHC runs without finding supersymmetric particles, the harder it becomes to believe the original elegant version of the idea. The hierarchy problem remains unsolved. The cancellations remain mysterious. The Higgs remains suspiciously light, and this is not the only suspicious number in the Standard Model. There is another one that sits at exactly 0 for no reason anyone can explain. The strong force is what holds the nucleus of an atom together. It is strong enough to overpower the electric repulsion between positively charged protons, which would otherwise blow every nucleus apart in an instant. The theory of the strong force is called quantum chromodynamics, and it is part of the Standard Model. It describes how quarks bind together into protons and neutrons through the exchange of particles called gluons. Now, when you write down the equations of quantum chromodynamics, you discover that there is a freedom in the theory. You can add a term to the equations, called the theta term, that describes how the strong force interacts with a particular kind of symmetry involving time reversal and parity. The size of this term is measured by a single number, often called theta bar. That number can in principle be anywhere between 0 and about 6.28, which is 2 pi. The strong force does not care what value theta bar takes. The equations work perfectly well for any value in that range. From a theoretical standpoint, no value is preferred. If theta bar were even moderately large, it would have observable consequences. The neutron would have an electric dipole moment, meaning its positive and negative charge distributions would be slightly separated in a specific direction. This dipole moment would be detectable. You would measure a tiny asymmetry in the neutron's response to electric fields, and from that asymmetry, you would be able to read off the value of theta bar. Physicists have been measuring the neutron's electric dipole moment for more than 60 years, with more and more sensitive experiments. They've never detected one. The upper limit is astonishingly small. Whatever theta bar is, it must be less than about 10 to the negative 10th. Less than a 10 billionth. Why is it so small? The equations allow any value. There is no mathematical reason for theta bar to be 0 rather than 1, or 3, or 6, and yet experimentally it sits at 0, or something so close to 0 that we cannot distinguish the two. This is the strong CP problem. CP stands for charge conjugation and parity, the two symmetries that the theta term would violate if it were non-zero. The problem is not that the Standard Model predicts theta bar wrong. The problem is that the Standard Model does not predict theta bar at all, and yet nature has chosen a value that is suspiciously, unnaturally small. Think of it like this. Imagine you walked into a room and saw a ball balanced perfectly on the tip of a pencil. You would not say, "How interesting, the laws of physics allow the ball to be there." You would say, "Something must be holding it in place, because this configuration is too precise to be an accident." That is how physicists feel about theta bar. It is too small to be an accident. There must be a mechanism that forces it to 0, or very close to 0. The Standard Model does not contain such a mechanism, so the mechanism, whatever it is, must come from beyond the Standard Model. The leading candidate for that mechanism is elegant, if slightly strange. It involves inventing an entirely new symmetry of nature, breaking it spontaneously, and letting the breaking generate a tiny new particle whose very existence dynamically drives theta bar to 0. That particle has a name. It has been searched for decades. It has never been found. But new experiments are about to get their first real chance. The mechanism is called the Pecquet-Quinn mechanism, named after the two physicists who proposed it in the 1970s. Here is the idea in plain language. Suppose you extend the standard model by adding a new symmetry. Not a symmetry of space like the rotational symmetries we know about, but an internal symmetry involving an extra field. The new field permeates all of space, like the Higgs field does. The symmetry requires that the field can take any value, and the physics does not care which value it takes. Now, suppose the symmetry gets broken. This happens naturally in the early universe as things cool down and the field settles into a particular value. When the symmetry breaks, a very light particle appears as a consequence. In quantum field theory, broken symmetries generically produce light particles called Goldstone bosons. The new particle in this case is called the axion. Here is the beautiful part. The axion is not just any particle. Because of the specific way it couples to the strong force, the axion field dynamically adjusts itself to cancel out the theta term. It is as if the theta bar parameter is no longer a fixed number but a variable, and the variable rolls downhill in its potential energy and settles at exactly zero, or as close to zero as the dynamics allow. The strong CP problem solves itself automatically as long as the axion exists. The price is that you have to postulate a new particle that nobody has seen, and the properties of this particle are quite specific. It must be extremely light, far lighter than any other known particle. It must interact extraordinarily weakly with ordinary matter. It must couple to photons in a particular very small way. These properties make the axion a fantastic candidate for dark matter. If there are enough axions in the universe, left over from the early moments after the Big Bang, they could account for the dark matter that experiments have failed to find using more conventional methods. The axion would not bump into atomic nuclei the way a WIMP would. It would permeate the galaxy as a kind of cosmic fluid, waiting to be found by a completely different kind of experiment. Those experiments exist now. The ADMX experiment at the University of Washington uses a tiny device called a microwave cavity, tuned to resonate at a very specific frequency. Inside a strong magnetic field, an axion passing through the cavity can convert into a photon at the resonant frequency. The signal would be extraordinarily faint, barely a whisper above the thermal noise of the detector. But by scanning slowly through different frequencies, the experiment can in principle detect an axion, if the axion's mass matches any of the frequencies it tests. Other experiments use different techniques. Caspar looks for the way an axion background would cause atomic nuclei to precess slightly. Haloscope experiments look for the conversion of axions into photons in large magnetic fields. A recent experiment called MADMAX is being built in Germany using a different cavity design. None of these experiments has found an axion yet, but the search is still in its early stages. Much of the parameter space where the axion could live is still unexplored. If the axion exists, it would solve two of the biggest mysteries in physics at once, the strong CP problem and dark matter. One particle, if it is real, would plug two holes in the standard model simultaneously. That would be enough to justify a lifetime of searching, but it would still leave untouched the most bewildering pattern in the theory. A pattern you see every time you write down the list of particles. Every fundamental matter particle in the standard model comes in 3 copies, not 2, not 4, 3. The first copy is the one you are made of, the up quark and the down quark, which together form protons and neutrons, the electron, which orbits around them, the electron neutrino, which occasionally emerges from nuclear reactions. 4 particles forming the first generation of matter. Then there is a second generation, the charm quark, heavier than the up quark, the strange quark, heavier than the down quark, the muon, heavier than the electron, the muon neutrino. These particles exist, but they are unstable. In the everyday world, they are produced in cosmic ray showers or in particle accelerators, and then they decay, usually within millionths of a second, into first-generation particles. And then there is a third generation, the top quark, which is so heavy it weighs as much as a gold atom despite being a single fundamental particle. The bottom quark, the tau, which is the heaviest known lepton, the tau neutrino. These are even shorter-lived and even more exotic. You do not encounter them in ordinary life. They appear in high-energy processes and vanish almost immediately. Here is the strange question. Why are there exactly 3 generations? The standard model does not require 3. The equations would work identically with 1 generation or 2 or 4 or 100. There is nothing in the structure of the theory that prefers 3, and yet every experiment that has ever been done to count the number of generations has converged on exactly 3. Measurements of the decay of the Z-boson at the LEP collider in the 1990s were particularly precise. They showed that there are exactly 3 types of ordinary neutrinos, which strongly suggests exactly 3 generations of matter. 3. Why? It gets stranger. The 3 generations are not just copies. They have wildly different masses. The top quark is about 35,000 times heavier than the up quark. The tau is about 3,500 times heavier than the electron. The pattern of masses plotted on a chart spans an enormous range that makes no obvious sense. There is no organizing principle, no simple rule that explains why the masses fall where they do. And the particles of different generations can turn into each other through the weak force, but they do so in a specific strange pattern. A chart called the CKM matrix for the quark case lists the probabilities for a quark of one flavor to transform into a quark of another flavor. The pattern shows that transitions within a generation are common, transitions between neighboring generations are less common, and transitions between distant generations are very rare. But again, the specific numbers in the chart are inputs to the theory, not outputs. The standard model measures them but does not explain them. This whole situation is called the flavor puzzle. It includes the number of generations, the pattern of masses, and the mixing between generations. It is one of the deepest unsolved questions in particle physics, and it has been sitting unsolved for more than 50 years. Various theories have tried to address it. Some propose that the quarks and leptons are not fundamental at all, but are composites of smaller particles whose interactions produce the observed pattern. Others propose extra symmetries, often called flavor symmetries, that constrain the possible mass patterns and explain why they look the way they do. None of these theories has been confirmed, and the heaviest particle in the whole collection, the top quark, carries some of the biggest clues of all. The top quark is the heaviest fundamental particle anyone has ever measured. It weighs about 173 times as much as a proton, which makes it roughly as heavy as an atom of tungsten. Not a chunk of tungsten, a single atom. All that mass packed into one point-like object with no internal structure we have been able to find. That weight is not just a curiosity. It is the reason the top quark matters so much for the entire standard model. Here is why. In quantum physics, heavy particles couple strongly to the Higgs field. The more a particle interacts with the Higgs, the heavier it becomes, and the larger its influence on the dynamics of the Higgs itself. The top quark interacts with the Higgs more powerfully than any other known particle. This single interaction dominates a great deal of Higgs physics. It determines, to a large extent, the corrections that the Higgs receives from virtual particles. It influences the calculation that says the Higgs should naturally weigh as much as the Planck scale. It drives the delicate balance that keeps the Higgs light. If the top quark were a little lighter or a little heavier, the structure of the Standard Model would shift in important ways. Think about what this means. The universe we live in, with its chemistry and its atoms and its long-lived stable structures, depends on the Higgs being roughly the mass it is. The Higgs being roughly the mass it is depends, through a long chain of quantum corrections, on the top quark being roughly its measured weight. And the top quark's weight is one of those 17 numbers we mentioned in the first chapter. The Standard Model has no explanation for it. You measure it, you feed it in, and if you had measured a slightly different value, the theory would describe a slightly different universe. Now consider the spread of masses across the 3 generations. The up quark weighs about 2/1000ths of a proton. The charm quark weighs about 1 1/3 protons. The top quark weighs 173 protons. These are not random numbers. They climb in a steady pattern, each generation much heavier than the last, and the pattern repeats roughly for the other particles. The electron, the muon, the tau, each about 200 times heavier than the last. The down quark, the strange quark, the bottom quark, each climbing a similar ladder. No one has ever explained this pattern. It looks organized. It is not random. It is not chaotic. It is a pattern, a rhythm, a progression. And yet the Standard Model, with all its precision and power, offers no mechanism for why the ladder exists, or why its rungs are spaced the way they are. Every mass is an independent input. The top quark sits at the top of this ladder, and because it is the heaviest, it responds most dramatically to the Higgs. Measurements of the top quark's mass have become precise enough to reveal something troubling. When you combine the measured masses of the Higgs and the top quark, and you ask what these values imply about the long-term stability of the quantum vacuum itself, the answer that comes back is unsettling. We'll get to that in a few chapters. For now, what matters is this. The top quark is the heaviest known fundamental particle. Its mass is unexplained. Its mass controls much of Higgs physics, and if even one of these generation masses were a little different, the universe could not exist in its current form. Why does the ladder have the spacing it has? The Standard Model is silent, but the pattern of mixing between generations may hold a clue. When quarks transform into each other, they do not do so randomly. The weak force allows a quark of one flavor to change into a quark of another flavor, emitting a W boson in the process. But the probabilities for these transitions follow a strict pattern, written down in a mathematical object called the CKM matrix. CKM stands for the initials of the 3 physicists who worked it out: Kabibo, Kobayashi, and Maskawa. The CKM matrix is a grid of 9 numbers. Each number represents the strength of a specific quark-to-quark transition, up to down, up to strange, up to bottom, and so on for the charm and top quarks. Physicists have been measuring these numbers for decades in collider experiments and in precise studies of particle decays. The numbers are now known to high accuracy. When you look at the finished grid, a pattern jumps out. The numbers along the diagonal, representing transitions within the same generation, are all very close to 1. An up quark almost always wants to become a down quark. A charm almost always becomes a strange. A top almost always becomes a bottom. These are the preferred transitions. The off-diagonal numbers representing transitions between different generations are much smaller. The transition from the first generation to the second is about 1/5 the strength of the within-generation transitions. The transition from the second generation to the third is about 1/20th, and the transition from the first generation to the third is smaller still, about 1/200th. Think of it like a staircase. Quarks move easily within their own step. They can step to the neighbouring step with some effort, and they can jump across multiple steps, only very rarely. Why does the matrix have this hierarchical structure? Why are the numbers arranged in this particular pattern of decreasing probabilities? The standard model does not say. It takes these numbers as inputs just as it takes the quark masses as inputs. You measure them, you feed them in, and the theory computes everything else correctly. There is a companion pattern for the leptons. The neutrino mixing matrix, called the PMNS matrix after Pontecorvo, Maki, Nakagawa, and Sakata, describes how one type of neutrino flavor converts into another as it travels. The PMNS matrix has its own 9 numbers, and it looks almost nothing like the CKM matrix. Where the quark matrix is strongly diagonal, the neutrino matrix is much more democratic. Neutrinos mix between generations with large probabilities. A muon neutrino can turn into a tau neutrino quite readily. The diagonal and off-diagonal elements of the PMNS matrix are all of comparable size, so the two matrices tell two very different stories. Quarks mix reluctantly between generations. Neutrinos mix freely. Why? The standard model has no answer. Physicists have proposed dozens of theories to explain these patterns. Some invoke additional symmetries that force the matrices to take specific shapes. Others propose that the quarks and leptons get their masses through different mechanisms, which naturally produce different mixing patterns. Still others suggest that the matrices are relics of physics at energy scales far beyond anything we can currently probe, and that the patterns we see are frozen shadows of dynamics we have not yet discovered. The CKM matrix also contains a complex phase, a number that encodes the amount of CP violation in the standard model. That phase is the source of the asymmetry between quarks and antiquarks that we discussed earlier. It is real. It is measurable, and as we said before, it is nowhere near large enough to explain the matter-antimatter imbalance of the universe. Which brings us back to the neutrinos. Their mixing matrix also has a CP violating phase, and that phase is still being measured in experiments that may take another decade to report their final results. Here is a strange fact about neutrinos. We know they have mass. We know the differences between the squared masses because neutrino oscillations depend on those differences. We know that the sum of the three masses is less than a certain small value because cosmological measurements place an upper bound. But we do not know the absolute value of any individual neutrino's mass. Nobody has ever directly weighed a neutrino. Other particles you can weigh. The electron's mass was measured in the late 1800s when J.J. Thomson deflected cathode rays with electric and magnetic fields and worked out the ratio of charge to mass. The proton was weighed not long after. Even exotic, short-lived particles like the muon and the tau have been weighed directly in laboratory experiments by watching their motion and measuring the energy and momentum of their decay products. The neutrino refuses to cooperate. It has no electric charge, so you cannot deflect it with electric fields. It has no color charge, so you cannot use the strong force to manipulate it. It responds only to gravity and the weak force, and both of these are too feeble to let you hold onto a neutrino long enough to weigh it directly. So physicists have been forced into indirect approaches. The most sensitive one involves watching a specific kind of radioactive decay. When tritium, a heavy form of hydrogen, decays, it emits an electron and an antineutrino. The energy of the electron, which you can measure precisely, depends on how much energy is carried away by the antineutrino. If the antineutrino has mass, The maximum possible electron energy is slightly reduced. The reduction is extremely small, but it is detectable. An experiment called Katrine in Germany is built around this principle. It uses a huge spectrometer, almost 80 feet long, to measure the electron energies from tritium decay with extraordinary precision. As of the most recent results, Katrine has established an upper limit on the electron-neutrino mass of less than 1 electron volt, which is about 2 million times lighter than the electron. Future data may push the limit down further. Another approach uses cosmology. The neutrinos from the early universe, the relic neutrino background, affected how matter clumped together on large scales. If neutrinos are heavier, they suppress the formation of small-scale structure. By measuring the distribution of galaxies and the cosmic microwave background, cosmologists can bound the sum of the three neutrino masses. The current limit from cosmology is roughly 1/10 of an electron volt for the sum of all three masses, which is tighter than any direct laboratory measurement. And there is a third approach, which would not just measure the mass but tell us something fundamental about the nature of the neutrino itself. It is the search for neutrinoless double beta decay. This is a hypothetical process in which two neutrons inside a nucleus decay simultaneously, emitting two electrons and no neutrinos at all. If this process is observed, it would mean the neutrino is its own antiparticle, a type of particle called a Majorana fermion. It would also indirectly measure the neutrino mass. Experiments around the world are hunting for this decay. Camland Zen in Japan uses a huge tank of liquid scintillator doped with xenon. Legend, being built now, will use germanium detectors. Nothing has been seen yet. The neutrino's mass is a window into physics beyond the standard model, and the difficulty of weighing it is a reminder of how little direct grip we have on a particle that is, by number, the most common massive particle in the universe. But the problem that has haunted theoretical physics the longest is not about any particle in the standard model at all. It is about the force the standard model does not describe. Gravity is the force you know best. It holds you to the ground. It keeps the moon circling the Earth and the Earth circling the sun. You feel it every second of your life. It is the only fundamental force that the standard model does not include. Let that land for a moment. The theory we have been calling the most successful theory in physics, the theory that describes every particle interaction we have ever measured, does not contain the one force you actually experience. General relativity, Einstein's theory of gravity, describes gravity beautifully at large scales. It predicts the motion of planets, the bending of light around massive objects, the existence of black holes, and the expansion of the universe. Its predictions have been confirmed by every experiment ever devised to test it, including the recent observations of gravitational waves from colliding black holes. It is, in its own domain, just as successful as the standard model is in its domain. But general relativity and the standard model do not talk to each other. They are formulated in completely different mathematical languages, built on completely different assumptions about the nature of reality. General relativity describes gravity as the curvature of a smooth, continuous space-time. Matter and energy bend space-time, and other matter moves along the curves. Everything in general relativity is deterministic and continuous. You can zoom in as much as you want, and the mathematics keeps working. The standard model describes forces as the exchange of quantum particles. Electromagnetic forces involve photons. The weak force involves W and Z bosons. The strong force involves gluons. Everything is quantum. Everything is probabilistic. And at the smallest scale, space and time themselves might not behave like the smooth continuum general relativity assumes. When physicists try to quantize gravity, to treat it the same way they treat the other forces, the math falls apart. The quantum corrections to gravitational interactions, calculated using the standard techniques of quantum field theory, produce infinities that cannot be removed. Every term in the calculation blows up, and the usual tricks for handling infinities, which work perfectly for the other forces, simply fail for gravity. The failure is not a small technical issue. It is a fundamental incompatibility between the two best theories in physics. This does not matter much in everyday life, or even in most of astrophysics, because gravity is extremely weak compared to the other forces. Two electrons repel each other electrically about 1 billion trillion times more strongly than they attract each other gravitationally. So in most situations you can ignore quantum gravity and either use the standard model or general relativity separately, depending on what you are studying. But there are two places where you cannot ignore it. The inside of a black hole, where matter is compressed to enormous density in a tiny volume, and the first moments after the Big Bang, when the entire universe was compressed into a region smaller than an atom. In both cases, you need a quantum theory of gravity to describe what is happening, and we do not have one, not a complete one, not a verified one. String theory has been the most popular candidate for half a century, proposing that all particles are actually tiny vibrating strings, and that the different vibrations produce the different particles we observe. String theory naturally includes gravity, and is mathematically consistent in certain formulations, but it has never made a prediction that has been tested experimentally, and it requires extra dimensions of space that we cannot observe. Another candidate is loop quantum gravity, which tries to quantize space-time directly, treating it as made of tiny discrete units at the smallest scales. Loop quantum gravity has produced interesting mathematical results, but has also not made testable predictions. The failure to unify gravity with the standard model is arguably the deepest problem in physics, and it becomes acute at a specific energy scale, the Planck scale, where gravity becomes as strong as the other forces. The Planck scale is the energy at which gravity stops being weak. It is where quantum effects and gravitational effects become comparable in strength, where the distinction between the two regimes breaks down, where our current theories simply cease to work. To reach the Planck scale, you would need to concentrate energy at a density that is almost inconceivable. A single Planck scale particle would weigh about 20 micrograms, which sounds small until you remember that this is the mass of a single fundamental point-like object. Compared to any particle we have ever created in a collider, the Planck scale is a factor of roughly 10 to the 15th higher in energy. That is 1,000,000 billion times more energetic than the most powerful collisions at the LHC. This gap between what we can test and where new physics becomes essential is called the energy desert. In the simplest extensions of the standard model, there's nothing interesting between the electroweak scale, which we can probe with colliders, and the Planck scale, which we cannot probe at all. The entire range of physics between these two scales might contain nothing new, or might contain vast architectures of particles and forces that we will never directly observe. The Planck scale also sets a natural length. If you convert the Planck energy into a wavelength using the usual rules of quantum mechanics, you get a length of about 1.6 times 10 to the negative 35th meters. That is the Planck length. It is the smallest distance at which our current physics can be reliably applied. At smaller scales, the usual description of space and time as a smooth continuum may simply cease to be accurate. What happens below the Planck length? Nobody knows. Perhaps space and time become discrete, quantized into tiny chunks. Perhaps they develop a foam-like structure, with the geometry of space-time itself fluctuating chaotically. Perhaps there are extra dimensions that become relevant. Perhaps the concepts of space and time simply do not apply at all, and something more fundamental takes over. The Planck scale is also suspicious in another way. It is roughly where, in many theoretical scenarios, all the forces of nature come together and become aspects of a single unified force. The strong force, the weak force, and electromagnetism already become closer in strength at high energies, in a way that suggests they might meet at a very high scale. Extend the trend to the Planck scale, and gravity joins them. This is the dream of a theory of everything, a single, unified description of all four forces. But this dream is, for now, only a dream. The gap between our experiments and the Planck scale is so vast that any direct test is essentially impossible. Even indirect tests are difficult. Cosmological observations can probe physics at high energies through the imprint left on the cosmic microwave background or through the formation of galaxies, but the constraints they provide are not precise enough to pick out a specific theory of quantum gravity, so we are in a peculiar position. We know the standard model cannot be the final theory, because it does not include gravity, and because it cannot explain dark matter, dark energy, or the matter-antimatter asymmetry. We know there must be new physics somewhere. We know the Planck scale is where that new physics must, at the very latest, kick in. And we have essentially no way to probe the Planck scale directly. The wall at the end of physics is real. We can see its shadow in our equations. We just cannot reach across it. And the shadow is darkest around the most extreme objects in the universe. A black hole is the place where gravity wins. Inside a black hole, the gravitational pull is so intense that not even light can escape. There is a boundary around every black hole called the event horizon. Anything that crosses the horizon, matter, light, information, is trapped inside, pulled inevitably toward the center. Black holes are real. We have imaged them. The Event Horizon Telescope produced a picture of the supermassive black hole at the center of our galaxy in 2022, showing a dark disk surrounded by a ring of glowing matter. Gravitational wave detectors have observed many black holes colliding and merging across the universe. They exist. They behave, on large scales, exactly the way general relativity predicts. And they are paradox machines when you try to combine general relativity with quantum mechanics. In the 1970s, Stephen Hawking showed that black holes are not completely black. Because of quantum effects near the event horizon, black holes should emit a faint thermal radiation. The radiation is now called Hawking radiation, and it causes black holes to slowly lose mass over time. A typical black hole formed from a collapsed star would take far longer than the age of the universe to evaporate completely. But smaller black holes would evaporate faster. A black hole the mass of a mountain would evaporate in about the current age of the universe. Hawking radiation is not controversial. Most physicists believe it is real, even though it is too faint to be observed for any known black hole. What is controversial is what it means. Here is the problem. When matter falls into a black hole, the matter carries information. The specific arrangement of particles, the quantum states, the identities of the molecules, all of that is information. In quantum mechanics, information is supposed to be conserved. You can scramble it, you can hide it, but you cannot destroy it. The quantum state of a closed system evolves in a way that, in principle, lets you reconstruct the initial state from the final state. But if a black hole radiates away all its mass as Hawking radiation, and if the Hawking radiation does not carry any information about what originally fell in, then the information that went into the black hole has been destroyed. The initial state cannot be recovered. Quantum mechanics appears to have been violated. This is the black hole information paradox. It has been a central puzzle in theoretical physics for nearly 50 years. Some physicists have argued that the Hawking radiation must, in some subtle way, carry the information out. Others have argued that the black hole leaves behind a remnant at the end of its evaporation, a tiny object that still contains all the original information. Still others have argued that the information is somehow encoded on the surface of the black hole in a way that is mathematically analogous to the hologram we associate with the tiny images on a credit card. This last idea, called the holographic principle, has developed into one of the most productive research programs in theoretical physics. Recent work, particularly in the context of string theory, and a framework called the ADS/CFT correspondence, suggests that the information does indeed come out. The details are subtle and mathematically intricate, but the broad picture is that quantum mechanics wins, and the information that seemed to be lost is in fact encoded in the radiation. But this resolution requires techniques and ideas that are well outside the standard model. It requires a quantum theory of gravity. It requires, in many formulations, extra dimensions or holographic encodings or other exotic features. The black hole information paradox is, in a sense, the standard model's limits being rubbed in our faces. The theory simply does not apply to the most extreme objects in the universe, and when we try to understand those objects, we are forced to reach for theories we do not yet have. And while black holes sit at one extreme, the most ordinary particles in your body may not be as stable as we think. You are made of protons and neutrons. Every atom in your body contains them. They sit at the core of every nucleus, bound together by the strong force, providing the mass that makes your body heavy. Protons are stable. As far as anyone has ever been able to measure, a proton just keeps on being a proton. It does not decay. It does not fall apart into lighter particles. If you isolate a proton in a clean environment, it sits there, apparently forever. In the standard model, this stability is built in. The proton is the lightest particle that carries something called baryon number. Because baryon number appears to be conserved in every process we have ever observed, the proton has nothing to decay into. It cannot spontaneously turn into something lighter because nothing lighter carries the same baryon number, so it persists. But baryon number conservation is what physicists call an accidental symmetry. It is not a deep feature of the theory. It emerges as a consequence of the specific particle content and interactions we've written down, rather than being imposed by a fundamental principle. In more ambitious theories, grand unified theories that merge the strong, weak and electromagnetic forces into a single unified force, baryon number is no longer exactly conserved. Protons can decay, slowly, very slowly, but not forever. The predicted lifetime depends on the specific theory, but it is typically something like 10 to the 34th years or longer. The universe is about 10 to the 10th years old, so you would have to wait a trillion times the current age of the universe to see a typical proton decay. You cannot wait that long, but you can watch a huge number of protons simultaneously. If you have, say, 10 to the 34th protons, then on average you should see roughly one decay per year, and you can easily gather 10 to the 34th protons by filling a tank with 50,000 tons of ultra-pure water. That is exactly what the Super Kamiokande experiment in Japan has been doing for more than 2 decades. A cylindrical tank buried deep underground, filled with 50,000 tons of water, surrounded by 11,000 photomultiplier tubes, watching for the faint flashes of light that would signal a decaying proton. Other experiments, like the upcoming Hyper Kamiokande and Dune, are being built to extend the search. So far, no confirmed proton decay has been observed. The limits on the proton's lifetime have been pushed higher and higher. The current limit is about 10 to the 34th years for the most commonly predicted decay mode, into a positron and a neutral pion. This limit has already ruled out the simplest grand unified theories, which predicted faster decays. More complicated theories predict longer lifetimes that the experiments have not yet reached. So proton decay is still a live possibility. If a single event were seen, it would be revolutionary. It would prove that baryon number is not exactly conserved. It would establish that protons, the foundation of ordinary matter, are mortal. It would provide direct evidence for physics at energy scales far beyond anything we can create in a collider. And it would matter for another reason. Proton decay is one of the natural ways to produce a matter-antimatter asymmetry in the early universe. If protons can decay in ways that violate baryon number, then the reverse process, the creation of protons without creating equal numbers of antiprotons, can also happen. This ties proton decay to one of the deepest mysteries we have already discussed. The excess of matter over antimatter that lets you exist might be directly connected to the slow, hidden instability of the protons inside your atoms. But proton decay is not the only kind of instability the Standard Model hints at. There's another, more alarming possibility involving the very vacuum of space. In physics, a stable state is one that has the lowest possible energy. Push a ball to the bottom of a valley and it sits there. It does not roll uphill by itself, it is stable. But there are such things as locally stable states. A ball sitting in a small dip partway up a mountain is in what physicists call a metastable state. It sits there for now. It looks stable. It behaves stably. But if something disturbed it enough, it could roll over the edge of the small dip and tumble all the way down to a deeper valley. Is the universe in the true bottom or in a dip? This question is not abstract. It has a specific, calculable answer in the Standard Model, and the answer depends on the precisely measured masses of the Higgs boson and the top quark. The Higgs field, which fills all of space, has a potential energy that depends on its value. In the simplest picture, the potential has the shape of a smooth bowl with a minimum at the value the Higgs field currently takes. Everything sits at the bottom of that bowl. The universe is in its lowest energy state, which is stable, and nothing can go wrong. But when you calculate the potential carefully, including quantum corrections from the top quark and other particles, the shape of the bowl changes. The top quark, being so heavy, pushes the potential downward at large Higgs field values. At very high field values far beyond where the Higgs currently sits, the potential can actually become negative and continue dropping. If this is true, then our current Higgs value is not the bottom, it is in a dip. And somewhere far away in field space, there is a deeper minimum, a true bottom that the universe has not yet found. Whether this is the case depends sensitively on the masses. With the current best measurements of the Higgs mass and the top quark mass, the calculation places our universe in a specific region of parameter space called the metastable region. Not clearly stable, not clearly unstable, metastable. The universe is sitting in a dip. The lifetime of a metastable vacuum depends on how easy it is to tunnel from the dip to the true bottom. This is a quantum mechanical process. At any point in space, there is a small probability for a bubble of true vacuum to spontaneously form, surrounded by a wall, and then expand outward at nearly the speed of light. Inside the bubble, the laws of physics would be different. Particle masses would be different. Ordinary atoms, as we know them, would not exist inside the bubble. When physicists calculate the expected lifetime of the electroweak vacuum given current measurements, the answer is a staggering number of years, much longer than the current age of the universe. So we are not in immediate danger. The vacuum has been sitting in its dip for nearly 14 billion years, and it shows every sign of continuing to sit there for a very long time. But this is a probabilistic statement. The calculation gives an average lifetime, not a guaranteed one, and the calculation assumes the standard model is exactly right. New physics at higher energy scales could change the shape of the Higgs potential and make the vacuum either more or less stable. The precise conclusion depends on the values of the Higgs and top quark masses at a level of precision that we are just beginning to reach. Future measurements will sharpen the picture, but the basic result is already striking. The universe appears to be balanced on a knife's edge between stability and instability for no reason anyone understands. Why is the universe so close to the boundary? That is a coincidence the standard model once again cannot explain. Suppose the electroweak vacuum does tunnel. Suppose, somewhere in the universe, right now or in 1 trillion years, a microscopic bubble of true vacuum spontaneously forms. What happens next is one of the strangest scenarios in physics. The bubble would be tiny at first, perhaps 1/1,000,000th of a meter across, or smaller. Inside the bubble, the Higgs field would have a different value. The masses of all particles would be different. Atoms, as we know them, would not exist inside. Electromagnetism, the weak force, and the strong force would have different effective strengths and structures. The bubble would then expand. Because the interior has lower energy than the exterior, there is a pressure pushing the wall outward. The wall accelerates. Within an incredibly short time, the wall would be moving at essentially the speed of light. Everything the bubble wall encountered would be converted into the new vacuum. Stars, planets, living beings, atoms, everything. The Higgs field inside would simply have a different value, and the chemistry and physics that keep ordinary matter structured would no longer apply. The transformation would be instantaneous and complete for anything inside the bubble. Because the wall moves at the speed of light, you would never see it coming. The light that would warn you of the bubble is travelling with the bubble. You would have no time to observe it, no time to react, no time to notice anything at all. One moment, ordinary physics, the next moment, a different universe. From your perspective, nothing in between. This is the worst-case scenario of vacuum decay. It is, in technical terms, a first-order phase transition in the Higgs field, propagating at the speed of light. Is this actually going to happen? The calculations, as we said, give a very long expected lifetime, much longer than the age of the universe, so the most likely answer is that no bubble will form in our observable patch of the universe for a very long time. But the probability is not zero. It is just extremely small. There is another consideration. The bubble would only convert the universe locally. Because the bubble expands at the speed of light, it can only affect regions within its past light cone at any given moment. Distant galaxies, beyond the bubble's reach, would continue with ordinary physics until the bubble arrived. And because the universe is expanding, some galaxies are receding from us so fast that the bubble could never reach them. They would be safe. Or rather, their corresponding bubbles forming independently in their own regions of space would be the threats to worry about. This scenario is sometimes called the death of the universe by vacuum decay. It is speculative. It relies on extrapolating the standard model into energy regimes we've not directly tested. New physics could stabilize the vacuum, or destabilize it further. But the bare calculation, using only the standard model as currently written, suggests we are sitting in a metastable configuration, waiting for a quantum tunneling event that might or might not ever happen. The fact that the universe appears to be in this precarious state is, to many physicists, a clue that the Higgs potential is not what the standard model alone predicts. A clue that new physics stabilizes things, or that the measured values of the Higgs and top quark masses are pointing towards something deeper. And one of the particles that might change this picture is a fourth kind of neutrino, a kind the standard model says should not exist at all. The standard model contains three kinds of neutrinos: electron, muon and tau. Each one is paired with a charged lepton, and each couples to the weak force in a specific way. Since the 1990s, a handful of experiments have reported results that do not fit into this simple three-neutrino picture. The most famous came from the liquid scintillator neutrino detector at Los Alamos, called LSND, which in the 90s observed more electron antineutrino-like events in a beam of muon antineutrinos than could be explained by ordinary three-neutrino oscillations. The excess looked as if muon neutrinos were occasionally transforming into electron neutrinos, much more readily than the standard picture allowed. A natural way to explain the LSND result is to introduce a fourth kind of neutrino, called a sterile neutrino. The word sterile, in this context, means that this neutrino does not couple to the weak force at all. It interacts only through gravity and through oscillation with the ordinary neutrinos. It is essentially a ghost of a ghost, a partner to the already almost undetectable regular neutrinos. If sterile neutrinos exist with the right mass and mixing properties, they could explain the LSND excess. They could also contribute to the mass of ordinary neutrinos through the seesaw mechanism. They could even be a component of dark matter if their mass is in the right range. Other experiments have since reported results that are consistent with sterile neutrinos, at least in certain analyses. Reactor neutrino experiments in some measurements have seen fewer neutrinos than expected, a discrepancy called the reactor antineutrino anomaly. Radioactive source experiments have seen fewer neutrinos than expected, called the gallium anomaly. The mini-boon experiment at Fermilab, running for over a decade, reported an excess of electron-neutrino-like events that in many interpretations points towards sterile neutrinos with properties similar to those that would explain LSND. And other experiments have reported no evidence for sterile neutrinos. The IceCube Observatory, which detects neutrinos passing through the South Pole ice, has placed limits on sterile neutrino mixing that rule out some of the parameter space that LSND and mini-boon suggested. The Minos and Diabé experiments have also produced constraints. The result is a tangled situation. Some experiments see hints, other experiments see nothing. The hints and the nothings are in tension with each other, and no single coherent picture has emerged. Either sterile neutrinos exist with very specific properties that let some experiments see them while others miss them, or the hints are due to misunderstood backgrounds or systematic effects that have not yet been identified. A new generation of experiments has been built to try to resolve the question. Short baseline neutrino experiments at Fermilab, including SBND and microboon, are specifically designed to confirm or rule out the mini-boon excess. Reactor experiments with very short baselines are testing the reactor anomaly more precisely. The outcome, over the next few years, will either establish that a fourth kind of neutrino exists, or show that the anomalies were artifacts. If sterile neutrinos are confirmed, it will be a major discovery. It would expand the neutrino sector beyond what the standard model contains. It would open a new window into physics at higher energy scales, since the sterile neutrino would likely be related to the heavy, right-handed neutrinos needed for the seesaw mechanism, and it would provide a potential new component of dark matter. If sterile neutrinos are definitively ruled out, the anomalies will be resolved as misunderstood systematic effects, and the three-neutrino picture will continue to hold. Either way, we're not far from an answer. We have mentioned several times now that the standard model requires about 17 numbers as inputs. Let us look at what those numbers actually are, because the list reveals something important about how incomplete the theory is. There is the mass of the electron, the mass of the muon, the mass of the tau, the masses of the 6 quarks. That is already 9 numbers, and none of them is explained by the theory. They are measured, and they are used, but they are not derived from any deeper principle. Then there are the 3 mixing angles and 1 complex phase in the CKM matrix, which describe how quarks of different flavors transform into each other. 4 more numbers, none of them explained. Then there are the 3 mixing angles and 1 phase in the PMNS matrix, describing neutrino oscillations. 4 more numbers, also unexplained. Then there are the coupling strengths of the 3 forces, which describe how strong the electromagnetic, weak, and strong interactions are. 3 more numbers. Then there are the parameters of the Higgs sector, which set the mass of the Higgs boson and the value of the Higgs field in the vacuum. 2 more numbers. Then, depending on how you count neutrinos, and whether you include the theta bar parameter of the strong CP problem, you add a few more. Altogether, somewhere around 20 or 25 fundamental parameters, depending on the accounting. Each one must be measured experimentally. Each one has a specific value, and for each one, the standard model is silent about why that value is what it is. Consider the ratio of the electron mass to the proton mass. It is about 1 part in 1,800. This ratio determines a vast amount of chemistry and biology. If it were much larger, atoms would behave very differently. If it were much smaller, chemistry would also fail. The number matters enormously for the universe to support complex structures, but in the standard model, the electron mass and the proton mass are both just inputs. Neither is predicted. Their ratio is just the ratio of 2 numbers that happen to have the values they have. Or consider the fine structure constant, often denoted by the Greek letter alpha. Its value is about 1 over 137. This number sets the strength of electromagnetism. It appears in every atomic energy level, in the color of every chemical reaction, in the rate at which every excited atom emits light. The physicist Richard Feynman called it one of the greatest mysteries in physics. It is dimensionless. It does not depend on the choice of units. And yet we have no theory that predicts it. The point is that the standard model, as mathematically elegant as it is a parameterized description of nature rather than a true derivation. It tells us that if these numbers have these values, then the observed world follows. It does not tell us why these numbers. A truly fundamental theory would ideally predict all of these parameters from a smaller number of inputs, perhaps even from no free parameters at all. The dream of physics, going back to Einstein, is a theory in which the universe we observe is the only possible universe, or at least a universe determined by a small handful of fundamental principles. We are very far from that dream. The standard model, for all its success, is really a long list of parameters with a mathematical framework for tying them together. The parameters themselves are a mystery, and another mystery, one that has been refusing to go away, involves a property of the electron that the standard model predicts to be exactly 0. The electron is a point particle, as far as we can tell. It has no internal structure, no measurable size. In the Standard Model, the electron is treated as a mathematical point with certain properties, and everything we have ever measured about the electron is consistent with that picture. One of the properties an electron can have in principle is an electric dipole moment. A dipole moment is what you would get if the positive and negative sides of a charge distribution were slightly separated. For a point particle, this might sound strange, but quantum mechanics allows a particle to have a dipole moment as an intrinsic property, independent of any spatial structure. The Standard Model predicts that the electron's electric dipole moment is extraordinarily small, essentially zero for practical purposes. The prediction comes from the fact that the amount of CP violation in the Standard Model is itself very small, and the electron's dipole moment, which requires CP violation to exist, inherits that smallness. Many theories beyond the Standard Model predict a larger dipole moment. Supersymmetry, in its various forms, often predicts an electron dipole moment that is much larger than the Standard Model expectation. Theories of leptogenesis and new sources of CP violation typically predict dipole moments that could be detected by precision experiments. So measuring the electron's dipole moment is a very sensitive test of physics beyond the Standard Model. If you find a non-zero value, you have found evidence for new physics. If you find zero, you have ruled out a vast class of theories. Experiments have been measuring the electron dipole moment for decades, with ever-improving precision. The current leading experiment, using trapped molecules of hafnium fluoride at JILA in Colorado, has placed an upper limit on the electron's dipole moment that is astonishingly tight. The electron is round in this sense to a precision that is hard to convey. If you scaled the electron up to the size of the Earth, the deviation from perfect spherical symmetry would be less than the width of a human hair. This extraordinary roundness is a problem for many theoretical frameworks. Theories that invoke new heavy particles typically predict dipole moments at levels that the experiment should have seen by now. The fact that no dipole moment has been observed means that either the new particles do not exist at the scales predicted, or that their contributions to the dipole moment cancel each other out in ways that are not entirely natural. The constraint is particularly severe for theories that claim to explain the matter-antimatter asymmetry of the universe through new sources of CP violation. If you add new CP violation to explain the asymmetry, you usually also contribute to the electron dipole moment. The fact that the dipole moment has not been seen limits how much new CP violation you can add, which in turn limits how naturally you can explain the asymmetry. Next-generation experiments are being designed to push the sensitivity further, in some cases by orders of magnitude. If these experiments detect a non-zero dipole moment, the implications would ripple through physics. It would be a direct, unambiguous signal of new physics, independent of any specific model. If they continue to see zero, the puzzle deepens. Why is the electron so round? Why is the asymmetry so large without visible dipole moments? What combination of new physics could simultaneously produce the observed matter excess and hide itself from dipole moment experiments? The electron's perfect roundness is yet another example of a small number that is smaller than it should be. Like the theta bar parameter in the strong CP problem, like the cosmological constant, like the tuning of the Higgs mass. Small numbers that have no clear reason to be small are a recurring pattern in the Standard Model's gaps. And speaking of small things that have been stubbornly hard to measure, there is the proton itself. The proton is not a point. Unlike the electron, which shows no measurable size, the proton has a definite spatial extent. It is a composite object, made of quarks and gluons bound together by the strong force. Its size can be defined as the radius at which its charge distribution falls off, and this radius can be measured in various ways. Classically, you measure the proton's size by scattering electrons off it. Send a beam of high-energy electrons at a target containing hydrogen atoms, measure how the electrons are deflected, and from the scattering pattern, you can deduce how the proton's charge is distributed. This method has been used for more than 50 years, and it gives a proton radius of about 0.877 femtometers. A femtometer is a millionth of a billionth of a meter. The proton is tiny, but even at this scale its size can be measured precisely, and the number has been refined over many decades. There is another way to measure the proton's radius. You can use the proton as the nucleus of a hydrogen atom, and you can study the atomic energy levels. The orbital of the electron around the proton depends slightly on the proton size, because when the electron is very close to the proton, the charge distribution of the proton affects how the electron's energy is calculated. Precise measurements of hydrogen spectral lines, interpreted through the framework of quantum electrodynamics, give you another measurement of the proton's radius. For decades, these two methods agreed. The proton radius was known to be about 0.877 femtometers, with some uncertainty. Then, in 2010, a clever experiment at the Paul Scherrer Institute in Switzerland did something different. Instead of using ordinary hydrogen, they used muonic hydrogen. In muonic hydrogen, the electron is replaced by a muon, which is about 200 times heavier. The muon orbits much closer to the proton than the electron does, so the spectrum of muonic hydrogen is much more sensitive to the proton's size. The measurement was beautiful. The radius they extracted was 0.84 femtometers, smaller than the electron-based measurements by about 4%. 4% does not sound like much, but in a world where both numbers are supposed to be the same, it was a gaping discrepancy. The muon and the electron should, according to lepton universality, see the proton the same way. They did not. The muon saw a smaller proton than the electron did. This result, called the proton radius puzzle, caused a decade of confusion. Theorists proposed that the muon might couple differently to protons than the electron does, which would be a violation of lepton universality. Experimentalists went back and redid the electron measurements with higher precision. New measurements of the hydrogen spectrum were performed, giving updated values. Electron scattering experiments at lower energies were repeated. In the years since, the picture has shifted. Some new electron-based measurements have produced values closer to the muonic hydrogen result, while others have confirmed the older, larger value. The puzzle has softened. Most of the field now thinks the discrepancy is shrinking and may go away with better measurements. But some tension remains, and the question of whether the original electron measurements had unaccounted systematic errors, or whether there is genuinely new physics affecting the muon-proton interaction, is still debated. The proton radius puzzle is a small mystery in the scheme of things. It does not threaten the standard model the way the matter-antimatter asymmetry does, but it is a reminder that even the most precisely studied object in physics can surprise us, and it is a reminder that the consistency of measurements is its own form of evidence, and when measurements disagree, there is always a possibility that new physics is hiding in the gap. A similar kind of persistent small tension shows up in one of the most ancient cosmic measurements we can make: the amount of light elements produced in the first few minutes after the Big Bang. In the first 3 minutes after the Big Bang, the universe was hot enough for nuclear reactions to occur. Protons and neutrons fused together to form light nuclei, producing the chemical elements that would eventually see the first generation of stars. This process is called Big Bang nucleosynthesis, and it is one of the great triumphs of modern cosmology. The theory of Big Bang nucleosynthesis is clean and predictive. Given the densities and temperatures of the early universe, and given the nuclear reaction rates that have been measured in laboratories on Earth, you can calculate exactly what mixture of elements should have been produced. The calculation predicts that after the first few minutes, the universe should consist of about 75% hydrogen by mass, about 25% helium, a trace of deuterium, and smaller traces of helium-3 and lithium-7. The predictions agree with observations for most of these elements to remarkable precision. The helium abundance measured in pristine gas clouds matches the prediction. The deuterium abundance measured in ancient gas clouds matches the prediction. The lithium-7 abundance does not match. When astronomers measure lithium-7 in the atmospheres of the oldest, most pristine stars in our galaxy, the stars that were formed from gas that had been processed by very few previous stellar generations, they find an abundance that is about 3 times lower than the Big Bang nucleosynthesis prediction. The measurement and the theory disagree. This discrepancy is called the primordial lithium problem, or sometimes the cosmic lithium anomaly. It has been persistent for more than 2 decades. The prediction is robust, the measurements are careful, and yet the numbers do not agree. Several possible explanations have been proposed. One possibility is that the lithium in old stars is being depleted over time by some stellar process that moves lithium down to deeper layers of the star where it can be destroyed. This idea has some support from stellar physics, but the exact mechanism has been hard to pin down, and the amount of depletion needed to close the gap is larger than most models comfortably predict. Another possibility is that the nuclear reaction rates used in the Big Bang nucleosynthesis calculation are slightly wrong. New laboratory measurements of these rates have been performed over the years, and they have generally confirmed the expected values, but some uncertainty remains, and it is possible that a subtle error in one of the rates is responsible for the discrepancy. A more exotic possibility is that new physics in the early universe affected lithium production. New particles decaying in the first few minutes could have altered the reaction rates in ways that would bring the prediction closer to the observation. Various dark matter scenarios have been proposed along these lines. None has been confirmed. For now, the lithium problem sits as a persistent small tension between the standard model of cosmology and observation. It is not a crisis, it is a loose thread, and sometimes loose threads unravel much more than anyone expected. There is one more tension in cosmology that is much larger and much more troubling. It involves a measurement you have probably heard about, the rate at which the universe is expanding. The universe is expanding. This has been known since the 1920s, when Edwin Hubble measured the velocities of distant galaxies and found that they were all moving away from us, with the more distant ones moving faster. The rate of expansion is called the Hubble constant, and it is measured in units of kilometers per second per megaparsec. A megaparsec is a unit of distance roughly 3 million light-years. So the Hubble constant tells you how fast, on average, a galaxy 3 million light-years away is receding from us. Measuring this rate accurately is one of the most important tasks in cosmology, because the Hubble constant sets the age of the universe, the scale of cosmic distances, and the energy density of space. There are 2 main ways to measure the Hubble constant. The first way uses the cosmic microwave background, the faint radiation left over from the early universe. By measuring the pattern of tiny temperature variations in this radiation, you can reconstruct the conditions in the early universe and then extrapolate forward using the equations of cosmology to predict the current expansion rate. The Planck satellite, which mapped the cosmic microwave background in exquisite detail, gave a value for the Hubble constant of about 67 kilometers per second per megaparsec. The second way uses the local universe. You measure the distances to nearby galaxies using a ladder of techniques, and you measure how fast those galaxies are moving away, and you combine the two to get the local expansion rate. The most careful modern measurement, using Cepheid variable stars in nearby galaxies and Type 1a supernovae in more distant ones, gives a value of about 73 kilometers per second per megaparsec. These two numbers do not agree. The difference is about 9%. And in a field where both measurements have claimed precisions of just a few percent, a 9% discrepancy is a major problem. This is the Hubble tension. It has been getting worse, not better, as the measurements have become more precise. If one of the measurements had been imprecise and the other had been accurate, you would expect the discrepancy to shrink as both measurements improved. Instead, both measurements have improved, and both continue to give different answers. Physicists have proposed many possible explanations. One possibility is that one of the measurements has a subtle systematic error that has not been identified. The Cepheid distance scale has been reviewed and refined many times, and the cosmic microwave background analysis has been checked thoroughly, but it is still possible that an error exists somewhere. Another possibility is that the universe contains additional physics that affects the early expansion rate, a component called early dark energy, which would have been important in the first few 100,000 years after the Big Bang and then faded away, could in principle resolve the tension. But adding such a component tends to create new tensions elsewhere, so the fit is not clean. A third possibility is that dark energy is not exactly a cosmological constant, but something slightly different. Evolving dark energy, whose density changes over time, could affect the inferred Hubble constant in specific ways. Recent results from the DESI survey, which measures the clustering of galaxies over vast volumes, have actually suggested some tension with a simple cosmological constant, though whether this is enough to resolve the Hubble tension is still being debated. Whatever the resolution turns out to be, the Hubble tension is the most prominent current anomaly in cosmology. And cosmology is, at its base, the standard model applied to the whole universe. If there is something wrong with cosmology, there is something wrong with our standard model of physics. The cracks are not hypothetical, they are here in the data now. We've walked through many cracks. The muon's wobble, which nearly cracked the standard model wide open before the theory caught up. The W boson mass measurement that still refuses to reconcile. The lepton universality test that flickered and mostly faded. The neutrino masses that have no place in the original theory. The matter-antimatter asymmetry that demands new physics. The dark matter that takes up 85% of matter and has never been directly detected. The dark energy that makes up 70% of everything and is a million billion 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 times smaller than the theory predicts. The hierarchy problem, the strong CP problem, the pattern of 3 generations, the gap to the Planck scale, the black hole information paradox, the metastable vacuum, the Hubble tension. None of these taken alone is a proof that the standard model is wrong. The standard model is not wrong. Every prediction it makes about particle collisions, every atomic energy level, every nuclear process we can calculate comes out right. The theory works. What it does not do is explain enough. The list of things it takes as input is too long. The list of things it does not describe is too long. The number of tiny coincidences it relies on is too large. A successor theory, whatever it turns out to be, would have to do several things at once. It would have to include gravity in a way that does not produce the infinities that plague the current approach. It would have to explain the origin of the particle masses and the mixing matrices rather than taking them as inputs. It would have to predict dark matter rather than being silent about it. It would have to explain why the cosmological constant is small rather than enormous. It would have to produce enough matter-antimatter asymmetry in the early universe to match observations. It would have to stabilize the Higgs mass, either through supersymmetry or through some other mechanism, or by showing that the hierarchy problem is somehow not a problem after all. These are a lot of requirements. No current candidate theory satisfies all of them. String theory addresses some, but has not made testable predictions. Supersymmetry addresses some, but has not been observed. Modifications of gravity address some, but often fail other tests. The honest answer is that we do not know what comes next. We know a successor theory is needed. We know roughly what it must do. We do not know what it looks like. But this is not a discouraging situation. It is one of the most exciting times to be thinking about physics. Every crack is a place where something new is hiding. Every unexplained number is a clue. Every anomaly that flickers and flickers again is the universe testing our ability to listen carefully. The Standard Model is the most successful theory ever written, and it is incomplete. These two statements are not in tension. They describe where we actually are. A great achievement built on 17 numbers and a beautiful mathematical structure, revealing by its own precision exactly where the edges of human knowledge lie. The work of the next generation of physicists is to find out what lies beyond those edges. The tools are being built. Bigger colliders, more sensitive detectors, better telescopes, deeper searches for dark matter and axions and sterile neutrinos and proton decay. Each one is a different way of listening to the silence, of reaching into the dark, of waiting for the universe to reveal its next clue. Somewhere in that silence, there is an answer. We are not sure what it will look like, but we know it is there, and when we find it, the cathedral gets a new foundation.